Ever tried listening to a phone call in a noisy cafe? The clinking cups, distant music, and chatter can turn a simple conversation into a frustrating guessing game. That's where speech enhancement steps in, using AI to clean up audio and make voices clearer. But here's the catch. Sometimes the very tools meant to fix the sound can create new problems. Imagine you're trying to restore a painting. If you're too aggressive, you might accidentally scrape off parts of the original artwork. Similarly, speech enhancement models can introduce artifacts, unwanted distortions that make audio sound unnatural. These artifacts can lower quality, make speech harder to understand, or even cause listener fatigue. This research tackles that issue with a clever two-step approach, inspired by a game you might know, golf. Think of the first stage as the approach shot, getting close to the hole. The second stage is the putt, the final precise stroke. Together they create a smoother, clearer result. Testing showed impressive improvements. Using metrics like PESQ, measuring perceptual quality, STOI, speech intelligibility, and CBAK, noise intrusiveness, the two-stage system outperformed single-model approaches. Graphs even showed that alternating stages reduced artifacts more effectively than applying the same model repeatedly. So what's the takeaway? By combining two specialized stages, like a golfer's approach and putt, this method offers a smarter way to clean up audio. It's faster, more accurate, and less prone to distortions. Whether you're streaming a podcast, watching a video, or relying on voice assistants, this research is quietly making your audio experience better. But how does this actually work under the hood? Let's dive into the technical heart of the PuttNet model. At its core is a convolutional-recurrent network, CRN, a type of AI that excels at processing sequential data like audio. Think of it as a team of detectives analyzing a crime scene. The CRN has two main parts, encoders and decoders. Encoders break down the messy audio into clues, while decoders piece those clues back together to form clearer speech. But here's the twist. They're connected by skip connections, which act like shortcuts to preserve important details. It's like making sure no critical evidence gets lost in the process. The input to the network isn't just one audio file, it's two. One is the noisy speech you hear, and the other is the enhanced version the model is trying to create. The network processes these together, like comparing a blurry photo to a sharp one to figure out what's missing. The output is a single, cleaner audio signal, essentially the model's best guess at what the speech should sound like. Now let's talk about the bottleneck in the middle, which uses Bi-LSTM layers. These are like traffic controllers, managing data flow to capture long-range patterns. Why does that matter? Regular convolutional networks, the building blocks of this model, are great at spotting local patterns, like sudden loud noises, but they struggle with low-frequency sounds that require looking further ahead. To fix this, the network adds dilated dense blocks. Think of them as wide-angle lenses that capture a broader temporal context, or longer stretches of audio. But here's where the magic happens, the approach and putt mechanisms. Imagine you're trying to fix a broken machine. The approach is your first pass, roughly aligning the parts. But sometimes it gets stuck in a trap, where it can't make progress. That's where putt comes in. It's like a second set of hands that nudges the system out of those stuck spots. But how do we even know if this works? Let's talk about how we measure progress in speech enhancement. Back in 2001, researchers introduced PESQ, or perceptual evaluation of speech quality. Think of it like a standardized test for speech clarity. Before PESQ, evaluating voice quality was subjective, like asking people, does this sound better? Now, PESQ uses math to simulate how humans perceive speech, giving engineers a reliable metric to tweak their models. Fast forward to modern deep learning. Data augmentation, like adding simulated background noise to training data, became a game changer. A 2020 study by Braun and Tashev showed that by exposing models to diverse noise scenarios, they became more robust. And in 2021, researchers improved on GANs, those neural networks that generate realistic speech, creating metric GAN+ to produce cleaner, more natural-sounding audio. These advancements aren't just academic. They're the invisible engines behind clearer phone calls, better voice assistants, and technologies that help people with hearing impairments. The PUT network we talked about earlier. It's built on these foundations, using waveform domain techniques to apply all these lessons in real time. So next time you hear a crisp, clear voice on a call, remember, it's the result of decades of research, from perceptual metrics to deep learning breakthroughs. The science of speech enhancement is evolving, and innovations like PuttNet are pushing the boundaries of what's possible. Stay tuned for more deep dives into the cutting edge of AI research, because the future of audio is just getting started.